Hello sir, we are from Group 8 from Section 3. And this is our organization chart. Ravindran as Project Manager, Kavitra as Structural Engineer, and me, Santeswaran, as an Architect. There are four objectives to our project. First of all, engage in a comparative evaluation between designs derived manually and those generated through software. Secondly, master skill of conducting manual structural design calculation. Thirdly, acquire practical proficiency with Tekla software for the purpose of structural analysis and design. Lastly, ensure that all design aspects comply with adequate specification. The purpose of our project is the project aims to enhance structural engineering skills by designing structural elements for a single story house using traditional hand methods and Tekla software following Eurocode standards. This approach helps understand traditional design practices and allows for a comparison between methods preparing for professional engineering challenges. As you can see here, this is our architecture layout for our project, following with structural layout ground plan. As you can see here, there are total 10 number of slabs here, and we applied 21 columns for our project for this plan.
Hello doctor, I am Ravindran Balamurugan. Chapter 3 Analysis of Action 3.1 Permanent and Variable Action. The information: slab thickness 150 mm, beam 200 by 500, characteristic strength of concrete 25 Newton per millimeter square, characteristic strength of steel 500 Newton per millimeter square. This is our permanent action and variable action for every slab. After find where permanent action and variable action, we can calculate design action. The design action formula is 1.35 GK plus 1.5 QK. We substitute into the formula. FS1 we got 4.82, FS2 is 5.82, FS3 is 4.82, FS4 is 5.36, FS5 is 6.86, FS6 is 4.07, FS7 is 5.26, FS8 is 6.86, FS9 is 6.86, FS10 is 5.60. Distribution of action. For distribution of action, formula is Ly over Lx. If the answer got more than 2, it's one-way slab. If the answer got below than 2, it's two-way slab. After substitute into the formula, we got FS1 1.96, FS2 is 1.91, FS3 is 1.17, FS4 is 1.04, FS5 is 1.19, FS6 is 1.35, FS7 is 1.27, FS8 is 1.19, FS9 is 3.23, FS10 is 3.28. FS1 until FS8 is two-way slab, and FS9 and FS10 is one-way slab. This is drawing for load distribution of action. Chapter 4 Design of Reinforced Concrete Beam. First, we need to find shear design and bending moment. For shear design, formula is WL over 2. W is width and L is length. After we substitute into the formula, we got FS1 is 10.64, FS2 is 10.72, and FS3 is 6.58, FS4 is 1.74, FS5 is 9.5, FS6 is 4.23, FS7 is 1.73, FS8 is 2.62, FS9 is 2.67, FS10 is 2.36. Secondly, the bending moment. Bending moment formula is WL square over 8. It's same. The W is width, L is length. After we substitute into the formula, is FS1 is 8.78, FS2 is 8.98, FS3 is 5.51, FS4 is 0.83, FS5 is 7.84, FS6 is 2.65, FS7 is 0.71, FS8 is 1.64, FS9 is 2.77, FS10 is 0.71. The unit is kilonewton per meter. 4.1 Roof beam. Before we find roof beam and ground beam, we need to find Z. For find the Z, we need to follow some steps. First step is ultimate moment resistance of section. Second step is natural exit depth. Third step is check maximum depth. And lastly, get the value of Z. For the example, we show the FS1 calculation. Firstly, ultimate moment resistance of section. The formula is 0.167 FCK. FCK is strength of concrete, and BD is the dimension of the beam. And we substitute into the formula, we got M bar is 208.75 kilonewton meter. M bar is the bigger than M, so it's singly reinforced. And secondly, we need to find natural existence. The formula is 0.454 FCK BX and D minus 0.4x, and we get x is two value. The first value is 1242 millimeter, and second value is 7 millimeter. We always take the small one, so we use x equals to 7 millimeter. After that, we check the maximum depth. We got the answer 0.01 for it's lower than 0.45. It's okay lah. And last one, we get nilai of z. The formula is z equals to d negative 0.4x. We substitute the x into the 7 as a 7. We got z equals to 497 millimeter. We repeat the procedure for find the value of z. So fs1 is we got 497, fs2 is 497, fs3 is 498, fs4 is 999, fs5 is 497, fs6 is 499, fs7 is 499, fs8 is 499, fs9 is 498, fs10 is 499. After find the value of z, we can find area of roof beam. The formula is Fs equals to m over 0.87 Fik is strength of steel z. We substitute into the formula, we got Fs1 42.49, Fs2 is 43.46, Fs3 is 26.67, and Fs4 is 4.16, Fs5 is 37.94, Fs6 is 12.83, Fs7 is 3.44, Fs8 is 8.08, Fs9 is 13.41, Fs10 is 3.44. 4.2, the area of ground beam. The formula is same, AS equals to m over 0.87 Fik z. The calculation for the FS1 is shown. The answer is 14.61 millimeter square. So we provide 1h8, and the area of provide is 15.3. And also we calculate the area of minimum and maximum. So the FS1 we got 110, and maximum is 4000. And we repeat the calculation to the another number of slab. Chapter 5, Design of Reinforced Concrete Column. The information: concrete grade C25, clear height 3650 mm, deep beam 450 mm, deep column 150 mm. The factor 0.75. The dimension of column is 300 by 300. Firstly, we need to find effective height. The formula for effective height is 0.75 by clear height, and also actual effective height, and the formula is LO over B. Secondly, we find limiting LO over B. The LO over B is finding for the column is slender or not. For find the limiting LO over B, we use B, H, FCK, and ED. B is base, H is height, FCK is strength of concrete, and ED is load. We substitute into the formula. We got FS1 is 90, FS2 is 89.7, FS3 is 114.46, FS4 is 222.59, FS5 is 95.26, FS6 is 142.76, FS7 is 223.23, FS8 is 181.40, FS9 is 179.7, FS10 is 191.13. Though all the column is not slender. Chapter 6, Design of Reinforced Concrete Slab. For find the design of main reinforced, we need to follow some steps. First step is we find the estimate thickness considering deflection control. Second one is bending moment. Third one is design of main reinforced. Fourth one is design of main reinforced. And lastly, we find the maximum and minimum area. Ground slab. This is example of calculation for the FS1. Firstly, we need to find the h equals to Lx over 20. And secondly, we need to find short span and long span. The formula is MSX and equals to ASX and LX square. For long span, ASY and LX square. We substitute, we got MSX is 6.15, MSY is 1.57. The effective depth, we got 160 millimeter, and we find the short span and long span area. For short span area is 100, 14.79, and long span is 31.61. This is answer for the another number of the slab. Here have short span and long span answer, and also provide the AS proof.
For the analysis, in this step-class structure model, we see a comprehensive structural analysis of a single-story building. The model features multiple horizontal beams, which were crucial for supporting the floors and roof and vertical columns, positions at the building's corners and internal points to bear and transfer loads to the foundation. The green lines represents the reinforcement details, showcasing the intricate connection and stability of the structure. Specifically, we can identify at least 8 primary columns and a composite network of beams on each floor, ensuring robust support and load distribution. This precise modeling enables efficient planning and analysis, optimizing the building safety and performance. The color-coded elements indicate structural performance: green for elements that pass the analysis, yellow for those that present warnings, and red for those that failed. Specifically, the model shows 181 elements passing, 35 elements with warnings. The warnings, which we already checked in some other videos, and it is already stated that the warnings in this element do not matter, and no failures in this view. This visualization helps identify potential issues and areas needing further attention, ensuring the building safety and structural integrity. This slide shows the column group design summary for static analysis. Each column group is identified by a reference code with critical members and stacks noted. For instance, CRC1 includes 5 columns with C12 as the critical member. All columns have a section of 300 by 300 and are grade C25 per 30, ensuring consistent material properties. The max utilization ratio is indicated, showing how efficiently each design utilizes the material. For example, CRC1 has a max UR of 0.603, well within accepted limits, and all columns have passed the design checks. This analysis confirms the structural integrity and reliability of our column design, ensuring safety in construction. This table display provides a summary of the beam group design for various references, including details such as the number of beams in each group, the critical member, spans, critical span, section dimension, grade, maximum utilization ratio, and the status of each beam. All beams are designed with a section size of 200 by 500 mm and a grade of C3240. The maximum utilization ratios vary, with some beams showing values close to or above the warning threshold, indicating potential areas that require further attention to ensure structural integrity. This analysis helps us identify critical beams and spans that need either reinforcement or resistance to meet safety standards. In this section, we examine the steel beam design analysis from TECLA. The table presented outlines the beam design summary, including the member references, group references, span section grades, lengths, number of connectors, camber utilization, and status for each steel beam. Each beam is designed with a section size of UB 203 by 133 by 25 mm and a grade of S355. The lengths of the beams vary and all have a chamber of 0.0. The utilization ratios indicate the efficiency of the beams under the applied loads, with all beams passing the design criteria. The analysis provides a comprehensive overview of the steel beam design, ensuring all structural elements meet safety and performance standards, which is crucial for the overall integrity and reliability of the construction. For the slab design analysis from TECLA, the table provided summarizes the slab map design detailing the level, slab reference type, thickness, grade, utilization, and status. All slabs are placed on beams at ground level with a thickness of 150 mm and a grade of C32 by 40. The utilization ratios for each slab indicate their efficiency under the applied loads, with all slabs passing the design criteria. This analysis ensures that the slabs meet the necessary structural performance standards, contributing to the overall stability and safety of the construction. This project aims to enhance the stability, strength, and serviceability of structures by verifying theoretical calculation and calculations made using TECLA software. The project's goal is to improve the quality of structures and reduce the risk of system failure. Key objectives include converting architectural layouts to structural layouts, analyzing actions on structures to determine variable and permanent actions, and calculating design actions and shear forces. The project also involved determining appropriate roof beams and ground beams, as well as the design of columns considering their slenderness. TECLA software ensures accuracy and precision, aligning with the project's objectives.